This is a titration problem where we're going to titrate a weak acid with a strong base. So the first question, and we're just going to kind of build on, each slide will have a different question on it. But the first one is, it wants the pH before any base is added. So first thing I want to do is write the equilibrium expression. And so I need a dissociation reaction. So I have HOCl, and it dissociates it as a weak acid into H plus and OCl minus. And so it wants a pH before we start, so I need an H plus. And so to be able to work that out, this is just a very simple acid problem. And so going back, we're making the assumption that the x that's subtracted and added is very, very small. And so we can basically use the formula that x squared over the initial concentration of the acid is going to equal to the Ka, where x is equal to our H plus, and so we can just minus log the x once we get that. So very quickly here, I'm just going to take the 3.5 times 10 to the minus 8 as my Ka. It's going to equal to x squared, and my initial concentration is 1 molar. So if I multiply by 1, and then therefore I'm just going to square root the 3.5 times 10 to the minus 8 and minus log that. So when I go through that process, then I end up with a pH of 3.73. Okay, so that's number one. Now, the next thing it wants to know is how many milliliters of NaOH must be added to reach the halfway point of a titration or the neutralization. So the first thing I look at is I have, again, let me kind of write the reaction. I'm going to make some shortcuts here and kind of show you that there's some really easy shortcuts you can do, but I'm just going to explain why. So whenever we neutralize, we're going to use up the acid and create the conjugate base. And so I know that I have 50 milliliters of 1 molar, and so I'm going to create millimoles. I know I have 50 millimoles of HOCl. Well, the halfway point is when half of that is gone, so I want to subtract 25 millimoles. Whenever I do that, I need 25 millimoles of OH to take the H away. It's just going to leave me 25 millimoles. So I know over here I'm going to have 25 millimoles of OCl minus in that reaction. So this is going to be, so I'm basically reacting the OH here, and so I'm going to end up with 25 millimoles of HOCl left, and that's the halfway point. Well, if I have 0.5 molar NaOH, and I want to end up with 25 millimoles, well, what do I need to multiply by? And so if I have 50 milliliters, 50 times 0.5 is going to give me 25 millimoles. And so the first question, how many milliliters of NaOH? The answer is 25 mils. Or 50 mils, sorry, 50 mils. Got 25 on the brain. So I need 50 mils of NaOH to produce those 25 millimoles to reach my halfway point. Now I can kind of do a little shortcut because I know now my total volume then, if I have 50 mils of my acid and 50 mils of my base, then I know I have 100 milliliters. And whenever we do an equilibrium expression, I know that I need molarities, not millimoles. So if I were to work out the rice on this, what I'm going to end up with is I know that this H plus is going to be my X. I know my HOCl is 25 over 100 plus X, but X is going to be so small I can ignore that. And I know that, so my plus X, but this is small, so I'm going to omit. And this is going to be 25 over 100 minus X, but again, I can omit. And so when I plug this into my equilibrium expression, I get my Ka, which, if we look at the top, I believe is 3.5 times 10 to the minus 8. is going to equal my x times 25 over 100 divided by my initial 25 over 100. And that's going to be my molarities. Now look what happens at the halfway point. That means that my acid and my conjugate base are the same value. And so honestly, if they ask you a question at the halfway point, I know that pH is equal to pKa as long as I'm neutralizing an acid, a weak acid. And so very easily, I can just take my Ka value and minus log, because that's going to be pKa, and that's going to give you my pH. And so when you work that through, if you minus log that value, you end up with 7.46. So the minus log of that is 7.46. So my pKa, 7.46, which is equal to pH. So there we go. That makes sense also because that's where, well, I am working my way up. Okay? So not quite at equilibrium or at the equivalence point. So now they want to know, what is the pH at the equivalence point? Well, what has to happen at the equivalence point? So again, I have my HOCl yielding my H plus OCl minus. Well, what's happening here is I have 50 millimoles of HOCl, so at my equivalence point, all of that is going to be gone. So I need 50 millimoles of OH to neutralize that, so I know I'm going to get 50 millimoles of OCl. So if I subtract from my acid, I add to my conjugate base, and this is 0. So basically now I have a new problem. Now I have my conjugate base. I have 50 millimoles of it, but I need molarity. So how much base made this happen? So again, I know it's 0.5 molar NaOH. I need it to be multiplied by something to equal 50 millimoles. So if I multiply that by 100 milliliters, then I know I need 100 milliliters of NaOH. So 100 mils of NaOH in my 50 mils of my HOCl is going to neutralize it. So my total volume is 150 milliliters. So if I take 50 and divide by 150, I get 0.333 molarity. But I don't have any HOCl, so now it becomes basically a salt hydrolysis problem. So I'm going to write this out. You really don't have to, but if we look at it, what ends up happening is now it's basic. So I know that if I have 0.33 molarity of OCl minus, I'm looking for the molarity of these two guys. And so both of those are x. So I need to solve for x. Well, what's this look like? Oh, it's an x squared over an initial problem, but it's equal to where x is equal to OH now. So at equilibrium, you just switch from acid to base. And so I need a Kb. Well, I know the Ka of this guy is 3.5 times 10 to the minus 8. And so we have a little formula that helps us figure this out. Ka times Kb is equal to 10 to the negative 14. So I know that Ka is 3.5 times 10 to the minus 8. And so what is my Kb? Well, if I just divide that, I can get my Kb. So I know that 10 to the negative 14 divided by 3.5 times 10 to the minus 8 is going to give me my Kb value. And so my Kb value comes out to be 2.86 times 10 to the minus 7. So again, at that equivalence point, you are back to an x squared over initial problem. The only difference is it is now a Kb. So if you were neutralizing the other way, a weak base with a strong acid, you would change from a Kb to a Ka. And so if I solve this then, if I multiply by 0.33, this is my molarity, take the square root, That's going to give me my OH value. So my OH value is 3.07 times 10 to the minus 4. So I know that X, which equals OH minus, is equal to 3.07 times 10 to the minus 4. So then, if I minus log that, value, I'm going to get POH. My POH comes out to be 3.51, but it didn't ask for POH, it asked for pH. So I know that pH is equal to 14 minus my POH. So my pH value, which makes sense, it's above 7, it's 10.48. So that's the value of pH at the equivalence point. So again, what happens at that equivalence point is it's just back to an x squared over initial problem, but now it's KB instead of KA. And so we just need to find that value, but we had to know the initial also, and we figured that out, just kind of reviewing a little bit. We figured out that we had 50 millimoles, because how much reacted, that's how much was neutralized, over the total volume, and that gave me my initial concentration, so that's I. So then the last step is very simple. That means I'm totally neutralized, so all that's left is strong base. So all I need to do is find the remaining amount of strong base. Well, again, I'm back to 50 millimoles of HOCl, but now I have 120 times 0.5, because I'm adding 0.5, so 120 times 0.5, I have 60 millimoles of NaOH. So now NaOH is the winner. So 60, if we do a limiting reactant, I have 60 millimoles of NaOH, or OH minus 50, because I have, that's of the HOCl, that reacts it out, that's gone. It's all used up. So what's my remainder? I have 10 millimoles of OH minus. But again, I need a molarity, because I need to find the pH. And so what is it floating in? Well, again, I had 50 milliliters of acid. Now I have 120 milliliters. So my total volume is 170 milliliters. So 10 millimoles divided by 170 milliliters gets me to 0.0588 molarity of my OH minus. So very simply, we minus log that. So I minus log the 0.0588. What does that give me? It gives me POH. My POH value is 1.23. Subtract that from 14. So 14 minus 1.23. And so I end up with 12.77 is my pH. So just kind of making sure that you understand the steps. The first step before, so this is a weak acid titrated with a strong base. So before any base is added, it's just an x squared over the initial concentration of that acid is equal to Ka. At the halfway point, easiest point on the whole thing, my pKa is equal to my pH. At the equivalence, that's where moles of acid is equal to your moles of base. Then I know that I'm back to an x squared over initial problem, but now it's my conjugate. So it's my conjugate base is equal to Kb, where Ka divided into 1 times 10 to the minus 14 is going to be equal to that Kb value. And then number 4, this is when I'm totally neutralized, and so I can use my millimoles remaining excess of the base divided by the total volume. That's going to give me the molarity of the OH minus. So I can minus log the OH minus and find POH, and 14 minus POH is equal to pH. Now remember, you also have to do that on the equivalence because this is X is equal to OH minus at the equivalence point. So that's just how to do a titration.